Hi, my name is Castro-Martín and I will be presenting on the use of modern machine learning methods to improve the estimation with data obtained with self-selection procedures. Over the last years, there has been an increase in the difficulty of collecting strict probability samples, mainly because they are expensive and people are more and more reluctant to participate in surveys over traditional methods. Therefore, online surveys have become very popular as a cheap and effective alternative. However, they imply important bias problems since their dependence on self-selection procedures causes an unknown propensity to participate. And also coverage problems are very frequent. In order to compensate this bias, some techniques like propensity score adjustment or statistical matching have been proposed. The common idea is using a reference probabilistic sample. Recent improvements over classical propensity score adjustment have been proposed lately, like kernel weighting, boosted kernel weighting, or the tree-based inverse propensity weighted estimator. So let's consider that we have a finite population. A subset of that population would be the online population that we have access to. From that online population, we extract a volunteer sample. The survey will have a variable of interest and some auxiliary variables. We also have a reference probabilistic sample, for which these auxiliary variables are known. And luckily, the weights for this reference sample are also known. In this situation, propensity score adjustments defines an indicator variable in order to estimate the propensity of participating in the survey, as you can see. These propensity scores are calculated training a machine learning model. For this model, both samples are combined. The target variable is the indicator variable, and the covariates are used as training data. Then the inverse of the estimated propensities are used as weights. The best machine learning algorithm for each case depends on the volunteering mechanism, but in general, logistic regression is the most reliable and the most used. You can see there its formula. It is pretty basic. So this method is well known for bias reduction. However, a study showed that its efficacy is likely to be partial and unpredictable. In a recent experiment, statistical matching showed better results. The tree-based inverse propensity weighted estimator applies PSA using a tree model instead of logistic regression. In a decision tree, split points are set based on the covariates until reaching a final estimation. The estimated propensity for each final node is the proportion between the number of non-probabilistic individuals and the number of probabilistic ones, taking the design weights into account. Kernel weighting uses the propensity scores to measure the distance among individuals from both samples. A zero-center kernel function is applied to smooth these distances. The final pseudo-weights are obtained considering the distance between each non-probabilistic individual and all the probabilistic ones. Statistical matching simply trains a machine learning model in order to predict the target variable. This model is trained using the volunteer sample and then applied to impute the values of the reference sample. Now that we have the original weights and the imputed values, the estimation is easy. Of course, any machine learning algorithm can be used. However, usually linear or logistic regression are chosen. As you can see, This estimation simply considers a linear dependence between the target variable and the covariates. What we propose is using a much more advanced algorithm like XGBooks. XGBooks represent the state of the art in machine learning because it is able to learn complex relations. But before getting into it, I also have to mention doubly robust estimators. They combine propensity score adjustment and matching with that formula. Again, it is usually applied with linear and logistic regressors. However, it could also be applied with other algorithms. We have recently proposed a more direct approach which simply uses PSA weights when training the matching models. This can be applied because most machine learning algorithms allow weighting the training data. As you can see, it isn't complicated. However, it can be very effective. As I said, XGBooks is a widely known state-of-the-art machine learning system. It is used in many winning solutions at Kaggle, a platform which hosts machine learning competitions. It works as a decision tree ensemble, which is optimized with gradient tree boosting, although it includes other improvements. When they work as an ensemble model, each tree returns a score and the prediction is the sum of the scores obtained. In order to determine the structure of the trees, this objective function is minimized. The first term measures the error of the estimation. It will usually be the square error for continuous variable or the logistic loss for binary variables. The second term penalizes complex trees to avoid overfitting. So our proposal is using XGBooks with statistical matching or with kernel weighting. It can also be combined with a standard propensity score adjustment in a doubly robust variant. Or we can use the PSA weights when training the XGBooks matching model. In order to test their performance, we have first conducted a study similar to chance. These three finite populations are generated. The first one is completely linear. The second one introduces a small nonlinear term, and the third one is the most nonlinear. The correction coefficient between the target variable with and without the error term can be adjusted. There are also three different models to determine the propensities for the non-probabilistic samples, again with increasing nonlinearity. So, a non-probabilistic sample of size 500 and a probabilistic sample of size 1000 are repeatedly drawn. 2000 simulations are run and the relative bias and mean square error are obtained. These are the results for the completely linear models. Of course, linear and logistic regression are theoretically unbeatable for these cases. Still, you can see that XGBoost is also able to learn the models. We cannot say the same for the method using a single tree. However, boosted kernel weighting, which is based on PSA and uses XGBoost, isn't working correctly either. We believe that the reason is overfitting. Hyperparameter optimization would be essential in order to solve this issue. In practice, models will rarely be linear, so let's move on to more difficult cases. As you can see, XGBoost keeps removing the bias where the others struggle. The same happens for the other nonlinear cases. However, we still can see that a single tree model is not effective enough and that boosted kernel weighting suffers a lot from overfitting. Seeing that simulated populations were too easy for the strongest methods, we conducted another study with real ones. The first population we use is the hotel booking demand dataset. It contains data of almost 120,000 bookings for a resort hotel and a city hotel. The target variable is the number of weeknights which are booked. Apart from that, 28 coverages are used in total. The non-probabilistic samples are obtained following two different strategies. For the first one, bookings from the resort hotel have 10 times more probability of being chosen, while for the second one, bookings from the city hotel have 5 times more probability of being chosen. The second population is called the adult dataset. It includes census income information for more than 30,000 adult individuals. The target variable is whether the individual makes over $50,000 a year. So, in this case, it is a binary variable instead of a continuous one. And 14 coverages are used for training. We use again two sampling strategies. For the first one, those who make over $50,000 a year have double probability of being chosen. For the second one, this is also multiplied by the square of the age. So, in these scenarios, the propensities depend on the target variable itself, and this dependence may not even be linear. The probabilistic samples are always obtained with simple random sampling. The size for both samples are 1,000, 2,000 and 5,000. Again, 2,000 simulations are run for each case. However, this time the relative rooted mean square error is obtained. We have chosen this metric simply because it is more representative of the error. Here you can see the results. XGBoost always performs better than its linear or single tree counterparts. Most times, the matching-based variants obtain the best results. However, for some specific cases, boosted kernel weighting is better. Again, this probably happens where the algorithm is not overlearning. With some proper hyperparameter optimization, the method should always behave correctly. So, in conclusion, it has been proven that using state-of-the-art machine learning algorithms can improve the results over using basic linear ones. In particular, XGBoost is a great example of that. However, its performance would be much more reliable if hyperparameter optimization were applied. We will explore this possibility in future works. These are the references cited through the presentation. And that will be all. Thanks a lot for your attention.